Okay, so let's get started. So hello everyone here in Bangalore. Good to be here. See you all live, and people back in Princeton. So we're starting at 6:30 p.m. here in India and 8 a.m. in the US. And the lectures will be there's 6 more lectures, including this one. That'll be Monday, Wednesday, Friday this week and next week. So we'll have lectures on Fridays, although we haven't had those before. And the format is very similar. I think there's 2 boards here that I'll write on, and the Zoom link is different, but everything else should be the same. And feel free to interrupt with questions. I think I should be able to hear you as I lecture on. Okay. Any questions from the audience here? All right. So I suspect there's some change in the audience, and not everyone is familiar with the things I've covered in the previous 20 lectures, hard to believe. But this part of the course will be relatively independent of what we talked about in the previous part. Although today's lecture will connect to things I talked about at the end of the previous lecture, although again, I'll try to make it somewhat self-contained. And so we'll talk about the Luttinger relation in various models of metals important for quantum condensed matter. And then we'll go on to sort of a different phase of the course where we'll talk about metallic phases without quasi-particle excitations. And quasi-particles are present everywhere in all the phases we talked about, not only in Fermi liquids, but also in the fractionalized phases where the partons became quasi-particles of different types. All right, so the model we're considering is the Anderson lattice model. It's supposed to be just a general model of electrons which are moving in 2 bands. So in some compound, like you say, uranium, beryllium-6, uranium, beryllium-13, you have the C electrons, which are called the conduction electrons, which are, say, on the beryllium atom. And then you have the D electrons, which are, say, on the uranium. So, and this is a very common situation in many compounds. And the difference between beryllium and uranium is that the orbital in uranium is much smaller. So the Coulomb interactions, the repulsion between 2 electrons on the same atom is much larger. So that's the general class of models we're considering, where there's strong correlations and strong interactions in one band, but not in the other. So here's a simple general model that you can imagine. You have the mobile electrons on the weakly correlated bands. Then you have the strong repulsion UD on the D sites of this band. They could even be hopping on the D sites, but I've just left it out. It's supposed to be weak. But what's definitely present is this hybridization, as it's called, W, between the 2 bands. So an electron hopping here can hop onto the W site, on the D site, and then come back. So the key property for our discussion today is the issue of conserved quantities, conserved densities in particular. So in this Hamiltonian only conserves the total density of all electrons. Which is, sum on I of C dagger I alpha Ci alpha plus D dagger I alpha Di alpha. So this is the only operator that commutes with this Hamiltonian. There's also the spin density, but I'm only going to talk about phases where the spin is not polarized. So the spin will just give a factor of 2 for most of the discussion. So that's the total conserved density. And as we discussed last time, it's these conserved densities that lead to the Luttinger relation. Okay, so for this implies, in particular, there's a Luttinger relation that says that there's a Fermi surface. There could be multiple Fermi surfaces. For simplicity, I'll just draw one Fermi surface. And the volume of this Fermi surface, let's call it VFS. And the Luttinger theorem would say that the volume of this Fermi surface divided by, well, 2 pi to the d with a factor of 2 for spin must equal the total density of electrons. And the total density, I'm just going to call for convenience for now as 1 plus rho c. The idea is that approximately, but not exactly, of course, there's 1 electron per site on the d orbital and rho c electrons per site of the c orbital. And the density is measured per unit cell volume, so it's a dimensionless number. So this should be equal to 1 plus rho c. And very important for our consideration today is the fact that this is mod 2. So the mod 2, because there could be completely filled bands that will not contribute to the Fermi surface, and a filled band, because of spin, can occupy 2 electrons. All right, so this is in fact an obvious and easy to verify statement for UD equals to 0. That's just counting of states for free electrons. So that's one way to make sure you got all the factors right. Just take them to be free electrons, and then you can figure out all the factors. But now the question, the non-trivial statement is that this holds to all order in UD. In the interaction. So if I start from the free fermion state and go all the way up to any order in UD, I discussed exactly how you can even define precisely the location of the Fermi surface momentum space, and the shape can change, but the volume is going to remain the same. Okay. All right. So this is a non-trivial experimental prediction. That no matter how large UD is, if I believe perturbation theory anyway, I'm going to see what's called the large Fermi surface. This you're going to call the large Fermi surface here. Large because it includes all the electrons. All right, so that's a highly non-trivial prediction, and it's been extremely successful. So you take many heavy fermion compounds, as they're called, and you measure the Fermi surface by various experiments, and to high accuracy, you find this works. All right, so that's a comforting situation, and people felt this meant that you could never violate this kind of sum rule. But now it's become clear in the last 20 years or so. There are also various experimental indications that I won't discuss here. With that, they can be other states of matter, metallic states of matter, where this is not true. Even though it holds to all orders in UD, at large UD, there's a possibility of getting other types of Fermi surfaces. And this is intimately connected to fractionalization and existence of spin liquids. And what I want to do today is give some indication of how that connection arises. All right. Okay, so now starting from this Anderson lattice model, you can also derive what's called the kondo lattice model. Okay, which I've also already discussed earlier. And this is the model where you do a canonical transformation, you do some kind of canonical transformation. And you get the kondo lattice model. And the general form of this is, let's call it H kondo lattice. Well, it's still got the first term, but everything else is going to be different. C dagger I alpha Cj alpha. But then you're going to get a kondo coupling, Ck, Jk, on sum on I, C dagger I sigma alpha beta, C I beta, dotted into S. I forget what I call this. Well, let me just call it Si, plus some Heisenberg coupling, say sum between nearest neighbors of Si dot Sj. And here, Si is a spinor half S equals 1/2 operator on each D site. All right, so this is the kondo lattice Hamiltonian, where what's happened is that at very large UD, if you look at this problem locally, what you find is that every D sites like to have exactly one electron in it. And so you just project onto the Hilbert space of states with exactly one electron on the D site. And then when you do the canonical transformation, you get some virtual higher order effects, higher order in W, which give you then some coupling between these spins sitting on the D sites and the conduction electrons, and also couplings between the D sites, which is this Heisenberg coupling. In this context, is sometimes called the RKKY coupling. And so this formally, at very large UD, this is an exact transformation. You can also keep higher order terms as you want. All you're doing is eliminating states by a canonical transformation, which are very high in energy. So near the Fermi surface or any reasonable experiment, this should be completely equivalent. Okay. And I've gone through some of the more explicit computations of JK and J, at least JK, in previous lectures. Okay, so now the question is, here I have an exact mapping of these two models. Do I reach the same conclusion on the structure of the Fermi surface? And the answer is you don't quite, and there's very different possibilities. So here again, the question you have to ask whenever faced with a problem of this type, and the fate of the Luttinger theorem, the question you have to ask is, what are the conserved quantities? So now here, the conserved density in this theory, the conserved densities look rather different. There's a conserved total density, conserved quantities. Well, there's just the density of electrons, the conduction band, sum on I, C dagger I alpha, Ci alpha. This commutes with the Hamiltonian because this obviously conserves the total number of electrons, and so does this. So there's no W term anymore. And so now your conserved quantity is the total number of electrons. But you also have another infinite set of conserved quantities. If I use a parton representation of the spins, so if I write Si, F dagger I alpha, sigma alpha beta, F I beta, I am using F rather than D to emphasize the fact that these Fs obey a relation constraint, Fi dagger alpha, Fi alpha, sum on I equals 1. So there's really here infinite number of conserved quantities, infinite number of conserved U1s, which is really the same thing as a gauge symmetry. So the original model only had a global charge symmetry. This one has many more symmetries. It has an infinite number of conserved quantities here, and the conserved charge is just the conduction electrons. All right. So now, in fact, from this point of view, in some way of thinking, this particular state is rather mysterious. It's not quite clear how it's going to appear from this formulation. So let's see what happens here. In the end, we believe the two models are the same, should describe the same low energy physics. It's just that what's obvious here is not so obvious here, and vice versa. Okay. Now I have to move this up. Okay, the other way. Okay. Yeah. Sorry? Thank you. Yeah, it's on every side. Thank you. Okay, so one thing, so let's think about the kondo lattice, first of all, in a different perturbation theory. In fact, what happens when you do the canonical transformation, this JK is about a 1 over U. And since U is large, maybe you should do a perturbation theory in JK. Now, when we did the kondo effect, we found that perturbation theory in JK was not well defined. JK went up to infinity under RG. But now we're not doing the kondo model, we're doing kondo lattice, and there's also this exchange coupling. So you can imagine something more exotic could happen. So let's consider the following situation where you have, let's take first JK equals 0, and say the spins are on some strange lattice, like say a triangular lattice. And the JH are exactly such that this forms, say, a spin liquid. So you get some spin liquid that we've studied in great detail. And to make life simple for us, let's even imagine it has a gap. Maybe it's a Z2 spin liquid with a gap. So that's what the F spins like to do. They form a spin liquid. And so at JK equals 0, this right now we're talking about, let's say at JK equals 0. So if we diagonalize this part of the Hamiltonian, we get the spin liquid. If you diagonalize this part of the Hamiltonian, I get a small Fermi surface. So this here, the size is determined by just rho C. That 1 has gone into the spin liquid. Okay. Okay, so this is the small Fermi surface. All right, so now you turn on a non-zero JK. So you have a coupling between these two, which is JK. And you can do perturbation theory in JK. Well, I won't go through it because there's some mean field calculation and notes that do effectively that. But it's quite easy to see when you do the perturbation theory that the usual proof of the Luttinger theorem, starting from JK equals 0, will also still work. The Luttinger theorem is a perturbative theorem, but you're free to decide which point to perturb from. Here we perturb from the free electron limit. Here we're going to perturb from the JK equals 0 limit. And so we can do the same perturbation theory. We'll get some Green's functions for these conduction electrons, which will have a self-energy, they'll obey the Luttinger-Watt theorem, and all of that will go through because those are very general constraints. And so we conclude here that all orders in perturbation theory in JK, not U, gives a small Fermi surface. Okay, so we seem to have violated the Luttinger relation. At least what we have violated is perturbation theory in U, but nobody said perturbation theory U had to work. Here's another regime where we're doing a different perturbation theory, and maybe that's sensible. And so this is obviously a different phase from that phase. So this violation has come at a price. And in fact, the purpose of today's lecture is to show you that price is something you have to pay. You can't violate it without paying the price. And the price you're paying is that in the spin liquid, there are fractionalized excitations with fractionalized excitation. Fractionalized neutral excitations with carry spin 1/2. Fractionalized neutral excitation, that is neutral in the electron density. Neutral excitations which carry a fractional spin but no charge. So these really have to be there. I'll try to convince you today to have any hope of violating the usual Luttinger theorem. Yeah.
So at K equal to 0, the spin liquid is sort of decoupled from the electrons, and the spin liquid, one can just look at the spin liquid and think that there is this extension of Lipschul's Matisse type of theorem, Oshikawa, Hastings
I'm going to talk about all of that.
Oh, okay, okay.
Yeah, that's the whole topic of the lecture.
Okay.
Yeah.
But I mean, at least at jk equal to 0, you so that is independently true for the spin liquid sector, and you are going to argue that the fallouts of that theorem continues for non-zero jk?
I think the way to think about this is that there are two different ways to do this, and I'm going to present both. One way that I'm presenting now is entirely self-contained and doesn't make any reference to the hosting Oshikawa and flux piercing in toruses. I'll talk about that, if time permits. But the way I'm doing it right now is I'm just taking an infinite system and I'm doing the usual Luttinger arguments that we went through in a previous lecture, but I'm not doing it in a more general context. Usually they're presented in a perturbation theory in U. Now I'm doing a perturbation theory in JK. So, I have some Green's function, GC for the conduction electrons, V omega minus EK minus some self energy of K and omega. And for the self energy, I can draw some graphs, which will have some C here, and there'll be a spin operator, and there'll be some spin-spin correlation functions that I need to know. Now, these are much harder to evaluate because I need to know the exact spin-spin correlation function in the spin liquid. But let's say in principle, I know all spin correlation functions in the spin liquid. Then I can just use the usual time-ordered perturbation theory and compute sigma, okay? And then because of the structure of this theory, I'm also very confident that this integral over d omega g d sigma d omega will be 0. Okay, so this is a perfectly self-contained argument and makes no reference to any topology. It's in the infinite volume limit. And it tells me that there is a stable state like this with a small Fermi surface and fractionalized excitations. So this is called the state, I guess I've already called it FL star. The star to remind you that there are these fractionalized excitations that must be present. All right, so this is to me a very satisfactory argument, but it relies on, again, like the old perturbation Luttinger theorem, it relies on some perturbative arguments, starting from some other limit. Okay, that may be, that's, some people are happy with that. I'm usually happy with it. But to really put the nail in the coffin, we can also give a non-perturbative argument, which I'll come to in the second part of this lecture. Okay. But here, one more thing I want to do, which I also mentioned last time, but going over it again, given the week break. You can now ask how in the kondo lattice theorem, so once you take this point of view, FL star seems like an obvious state. It wasn't obvious because nobody talked about it for the longest time, but it is obvious once you think about it the right way. But from this point of view then, how do you get the large Fermi surface? So from this perturbation theory, how are you going to get the other state? If this kondo lattice formulation, it gives us something new, well, okay, but why should I believe it? Can the kondo lattice formulation give me the other state? So let me quick review how that's done. Okay, so now, and there these symmetries will play an important role. Okay, so I think I'm going to erase this here because, okay. All right, so there's, let's make a little table of these charges here. So there are two symmetries. Let me see. And I did this, I'll make C here and F here. There's the U1 symmetry, which is the global U1 symmetry, in which C has a charge 1 and F has charge 0. And there's U1 gauge, where this is charge 0 and this is charge 1. Now, I applied Luttinger theorem in this argument to this U1 symmetry, and I came up with the conclusion that the Fermi surface volume should be small. You can also apply Luttinger arguments to U1 gauge, and they end up giving you some constraints on the spin-ons here. If the spin-ons have a Fermi surface, then there's a separate constraint of the size of the spin-on Fermi surface. So that's a constraint on the structure of the spin liquid, which is related to many things we discussed in the first part of the course. But yeah, I'll say a little bit more about that by the end of this lecture. All right. Okay, but now the question is, how do I get the large Fermi surface from this formulation? Well, the way you do it is, yes.
One-to-one mapping.
Use the mic.
So there is a one-to-one mapping between these two Hamiltonian, but
Right.
still violating Luttinger relations. This seems to be counterintuitive.
Yes.
So how to understand?
Well, that's what I'm trying to explain. So perturbation theory UD gives us one answer. Perturbation theory JK gives us another answer. Okay. So now I'm going to go beyond perturbation theory in JK and get the old answer.
Okay.
Okay. Now.
So this violations means is because I'm doing these perturbative calculations, and that's the issue here?
Nothing has been violated. Both are valid answers. In fact, the answer is there's two possibilities. The kondo lattice formulation is more powerful because it can show you both. The Hubbard model, the Anderson lattice formulation only seems to give you one. But that's a weakness in the perturbation theory, not in the model. Okay, the models are the same, and there are two phases, the FL and FL star. The Hubbard model, Anderson lattice formulation, the FL is obvious. In the FL star formulation, once you think this way, then FL star is, in the kondo lattice formulation, FL star is obvious. Now what I want to show you is that you can also get FL in the kondo lattice approach. Yeah. Any other question?
Yeah,
Right.
one more question.
Yeah, go ahead.
So if I put add interactions between the C electron also, so you mentioned the interaction is weak.
Yeah.
Then still Luttinger relation is valid?
Absolutely. You can add all kinds of terms.
Okay.
You know, this relation I just erased, integral d omega g d sigma d omega equals 0, is extremely general. You can throw almost anything to it. As long as you're doing a perturbation theory, it'll work. So the Fermi surface volume is a very robust thing in perturbation theory. It's just that here we're doing a rather unconventional perturbation theory. We're starting from a state. The spin liquid state has, you know, long range topological order of some type. And usually we don't start from such a complicated state as the 0th point of a perturbation state, but that's what we're doing.
Yeah. Thank you.
Okay. Okay, great. So now again, I have to recall, how do I do things non-perturbative in JK? So we had this large M mean field theory. So what I'm going to do now, not a perturbation theory in JK, I'm going to do perturbation theory in 1 over M, where, so that's yet another perturbation theory. So I have 3 perturbation theory. And in each perturbation theory, there is a Luttinger theorem that you can prove. You just have to decide which one you're going to prove. Okay, so now we do the large M mean field theory. Then we had a mean field Hamiltonian, which had various terms. It has the free electron terms. Epsilon k, C dagger k alpha, Ck alpha, plus you had some spin-on dispersion. Again, none of it matters here. K alpha. And the most important term was the following term, P I, okay. I probably get the signs wrong from the previous one, but it doesn't matter. Minus Pi minus emission conjugate. So this Pi was a Hubbard-Stratonovich field. So it's a Higgs field. And we are interested in the phase. So I can't write below this blue line. What we want to do is 1 over M expansion about the saddle point, about pi average not equal to 0. Okay, so what is this? This pi is an emergent boson.
Subir, what is the definition of M?
M is SU2 going to SUM.
I see.
Generalizes. Yeah, so this is spelled out in great detail in the notes, and I also worked it out on the board a few lectures ago. But yeah, thank you for reminding me. All right, so now I'm doing a third perturbation theory about a different point. I have a large M saddle point where I find that P bar can be 0. And then I do an expansion to all orders in 1 over M and try to prove a Luttinger theorem there. Okay. So here I want to make another column, which is P. So for this, so now this P has some strange charges. If C has charge 1, okay, so then P also has to have such charge 1 because the combination will have charge 0. So P has U1 charge 1. And it also has charge, the gate charge, which is -1. Okay. So it's a boson, which carries charges on both the global U1 and the gate U1. All right. And this boson is condensed. Okay. So now when a boson condenses, it's like a Higgs boson. When it condenses, it Higgses the gate symmetry, or by abuse of notation, people don't like it, but it breaks the gate symmetry. And once the gate symmetry is broken, there is no more Luttinger theorem left for you to work with. It's like in a Bose condensate. When you condense a boson, even for a Bose gas, there's no Luttinger theorem to worry about because the global U1 there has been broken by the Bose condensate. So there's a Bose condensate here. And so this P has broken the gate symmetry. But has it really? Well, so this is where you now see that there's there is another gate symmetry I can define, which is the diagonal gate symmetry. So I'll call it U1 diag. And under U1 diag, if I've got it right, the U1 diag is basically the gauge transformation where you transform U1 and U1 gauge together. Okay, so you just add up these charges. So you'll get 1, 1, 0. So there's a U1 diagonal gauge symmetry, which is just a gauge transformation with the gauge transformation is the same. It's global. The transformation is the same in this U1 gauge and U1 global. So this U1 diag is the sum of these two gauge fields. And so the P boson has charge 0. So U1 diag is not broken. So the correct gauge symmetry I should work with, the correct U1 symmetry I should work with is U1 diag. So if I want a Luttinger theorem, the Luttinger theorem should apply to U1 diag in this phase. So what does the Luttinger theorem say? It says, well, you have a Fermi surface, and the volume enclosed by the Fermi surface is the total charge. And what is the total charge? Well, the total charge is 1 plus 1. It counts both C and F. So that's the large Fermi surface. Okay, so that's how you get in the 1 over M expansion, the large Fermi surface. So I can say that here. Let me say that over here. So phase with P bar equals 0, not equal to 0, has U1 diag unbroken. So that means that the V of Fs, the volume of the Fermi surface, is large. Okay. So I have now proven in a different expansion in the kondo lattice model, in the 1 over M expansion, I have proven that the kondo lattice has the observed phase that I found in the Anderson lattice formulation. But I have also learned something new, that the Anderson lattice analysis was missing something. It is possible for either model, because it's the same model, to also have this FL star phase where the Fermi surface is small. So this is the FL phase. So what we see is that now we also see the nature of the phase transition between the FL and FL star. The nature of the phase transition is a phase transition involving Higgs condensation. You have a Higgs field P, which is condensed in the FL phase. So that's sort of analogous to the Higgs field in our universe, which is condensed in the, in the Weinberg-Salon model, and gives us the theory of weak interactions and fermion masses. In this case, the analog of the fermion masses is this term here, which mixes the C dagger F, and this is the hybridization. So the two bands mix, and that's completely analogous to the way the Higgs boson gives masses to the electron and other leptons by the condensation of P by the Higgs boson. So that's completely, here you don't get a gap, but you get a mixing that gives you a large Fermi surface. And the other phase where P is not condensed, well, then you really have to apply the, since when P is not condensed, then you have more constraints to worry about because you have more symmetries. And so there's this U1 that gives you the small Fermi surface, and this U1 gauge gives you all kinds of constraints in the structure of the spinlet. Yeah. Yes, go ahead, Juven.
Hi, Subir.
Hi.
Just to clarify the table, the three of U1. The first U1 is the global. The second U1 gauge is dynamical gauge. But the last one, the third one, the U1 diagonal is global, right?
Correct. It's global.
It's global. Yeah, it's global. That's what I think.
Yeah. I mean, what's relevant for Luttinger theorem is just global symmetries. But gauge, they can also be gauge. You just take the global subgroup of the gauge symmetry. All right, great. So, this could be end of story. The only unsatisfactory part about it, if you wish, is that all three arguments, I have three different proofs of Luttinger theorem here. One is perturbation in U, another is perturbation in JK, another is perturbation in 1 over M. They're all perturbative. But they're different perturbation theories, and the whole story hangs together. But I'll turn now to a different set of arguments that don't use any perturbation theory. I mean, they have their own assumptions and issues. They're not rigorous either. But that has the benefit of clarifying and also connecting better with things we learned in the first part of the course.
Question, if I may?
Yes.
So in one of these, you had a smaller Fermi surface.
Yes.
And it asked for kind of a correction term to correct the equation, which might be expressible in terms of the remaining degrees of freedom. Is there a way to do that?
That's what I'm going to discuss.
Okay,
yeah. Yeah, that's the what I'm going to discuss has that flavor. But these arguments are somewhat different. There is no correction term in the FL star phase. All orders in JK, there's no correction. At 0th order in JK, there's a small Fermi surface, and all orders in JK, it remains small, provided the spin liquid is, some reasonable ground state. If it has a gap, it's almost rigorous. If it's gapless, you can still prove it. Well, but the argument essentially goes through. Okay, all right. So we now will take another point of view, which relates to things Shubro asked about earlier, and also Nadia mentioned. We're going to take a more topological point of view, which has.
May I ask one question?
Yes, go ahead.
If the global U1 of C was also a gauge.
Yeah, I can't hear you.
Is it better?
Yeah, I can hear you now.
If the C gauge symmetry, the global. I'm sorry, my microphone is not working well. My microphone is not working. I will type the question. Maybe it will be better.
Okay, go ahead and type it while I get started on the other part. Okay, so. All right, so this argument that I'm going to present due to Oshikawa, who was in turn inspired by the Laughlin argument for the quantization of the Hall effect. And so there are, so it's connects very naturally to all these fractionalized phases that we have already discussed. Yeah, you're writing a question. Again, I can hear some various noises. Did you write your question online?
I'm writing. Just 1 moment.
Okay. All right. So yeah, let me erase that too. So Oshikawa's argument was initially for just proving Fermi is liquid, and the extension that I'll discuss later was done by Senthil and his co-authors, including me. All right, so let's first present Oshikawa's argument. Non-perturbative argument. Okay, so we take some lattice and we just imagine that we're in 2 dimensions on a square lattice, which has perfect translational symmetry. I'm also going to just ignore the spin. We'll just talk about spinless electrons with some density, with some interactions. And we're going to assume the ground state is a Fermi liquid. What that assumption entails, I'll come to in a minute. Yeah, okay, the question. If the global U1 symmetry of C fermion was also gauge symmetry, then the condensation of the answer is yes. Yeah, so I presume you can. Yeah, so the question was, if the global U1 symmetry is a gauge symmetry, will it gap one gauge field, the other one remain gapless? Yeah, I think the answer is yes. Okay. So coming back to Oshikawa's argument, you have a full translational symmetry, so discrete translated symmetry in the X and the Y direction. So we can define, if I have any state of the system, in particular the ground state, so if any state psi, eigenstates of the Hamiltonian, it's an eigenstate of translation by one lattice site. And so this must be some, which we'll call e to the IPX, the momentum times psi. So each state has an eigenvalue of translation, the full many-body state, and that we call the eigenvalue e to the IPX. Sorry, I need my cheat sheet to make sure I get everything right here. Okay, yeah, that's correct. All right, and PX, therefore, is only determined is mod 2 pi. And this is I'm going to take a unit lattice spacing here everywhere. Okay. All right. So the value of Px is only determined modulo 2 pi. Okay, now we consider the following thought experiment. We take this system and put it on a torus. And I'm just going to try one line of the torus here, because say this line here, and so the electrons are moving this way on a ring. I mean, it's not really a ring. I'm just taking periodic boundary conditions in this direction. So this is the X direction, say. And I'm just going to imagine for much of the argument, the Y direction doesn't play any role. So it's as if I just have a 1D fermions moving in a ring, perfect ring. Okay. And what I'm going to do is insert a flux phi in the center of this ring. So I'm going to take phi of t, and phi of t changes adiabatically from 0 to 2 pi. Okay, so this is all empty space here, just to emphasize. Here's my ring. I've just shown you one. It's a ring here. And this is where the electrons are. So there's no flux where the electrons are. the flux is entirely in the hole of the torus. Okay. So as I'm sure you know, the flux, once phi go to 2 pi, the final state is gauge equivalent to the original Hamiltonian. You can do a gauge transformation and get rid of this. It's a non-local gauge transformation. And really the whole game is understanding the effect of that non-local gauge transformation. So let's just consider, a simple tight banding model of electrons moving in this direction, and then the Hamiltonian would be cosine of be minus t c dagger I e to the I, the vector potential, which is a constant, e to the I plus x. So when you take a Fourier transform and put in the flux, it becomes minus 2t cosine of kx minus phi over L times c dagger k ck, where L is this length here. Oh, let me call it Lx. So it's this periodic boundary condition, it's Lx. Okay. All right, so you just choose a gauge where A is constant, and the line integral of A along this has to equal to phi. And so this is my Hamiltonian because the line integral of this, it's A is phi over L. Okay. And now you can see, at least in the free particle, this is, if you have only local interaction, this is the only place the flux appears. And you can see easily that what the statement I made earlier, then the flux is 2 pi. That's equivalent to just shifting all the k by 2 pi over L, because all the k in this condition are 2 pi nx over L. All right, so therefore you can make an exact statement. But first, let's make the statement for free particles, and then just wave our hands or go to the notes for a more careful argument that the statement also holds in the presence of interactions. So what happens here? As you change the flux phi very, very slowly. So let's make a picture of it. So you have a band here, and you have a bunch of states. Okay, so there's 2 points of view. One is that as you change phi, nothing changes. The value of k remains the same, but this phi just shifts the states by 2 pi. So you get another set of states where this is shifted by 2 pi. So let's see, the minimum will be at 2 pi. So okay, I'm going to exaggerate the shift here. Probably I shouldn't have put so many points. This whole thing, okay, maybe I'll just draw it here. There's something like this. Well, this goes like that. Okay, so everything is just shifted by 2 pi. And so this state goes over here, this state goes over here, this state goes over here. The energy changes. Okay, but now the important point is that the energy of this state here is the same as the energy of this state. These are supposed to be all horizontal to each other. Okay, so now there's a question of getting the gauge right. So in this gauge, where I've just changed phi from 0 to 2 pi, k doesn't change, but the energy of each single particle state changes. But they come back to a set of energies which are the same as the old set of energies. Now, what I want to do is compare the momentum of the system before and after I do the flux insertion. Now, for that to be a sensible comparison, since the 2 states systems are gauge equivalent, I should compare the momentum in the same gauge. Okay, so it should do a gauge transformation, which corresponds to getting rid of this phi. And you can see how to get rid of it, just shift kx by 2 pi over L. So this tells us, so in the same gauge, this eigenvalue of delta px changes, which is of course only mentioned modulo, measured modulo 2 pi. So delta px, before and after the Flux insertion, is 2 pi over L sub x. And then if I had a bunch of particles, the same thing apply to every particle. So I just multiplied by the number of particles, n mod 2 pi. So this is a completely rigorous argument with no assumptions whatsoever. It's just a question of looking at the commutation relations of the Hamiltonian with the translation operator in the presence of a flux. That's worked out in more detail in the notes. But the argument is very simple. You can just see it right here. It's only the kinetic energy that depends on the flux. All the interactions we assume are local. They conserve total momentum. So that doesn't change the change in total momentum. So there is a change in total momentum due to the flux insertion, which is exactly equal to 2 pi n over Lx. So this is an exact statement and a non-perturbative statement. True for any system. There is no ifs and ands and buts on this statement, provided you get your gauge transformations correct. Okay. All right, so now we have a very useful exact statement for the full Hamiltonian. Yes.
Should the flux phi be quantized in some way?
No, I'm just have some external magnetic field and I'm just slowly changing the flux. It's not quantized. I mean, I'm not considering a superconductor. Even in a superconductor, the flux is not quantized. It's just that it has minimum of energy at integer multiples of h over 2e.
So this modulo 2 pi, it can only shift by this certain amount. What does it say for the flux phi then?
Well, I do an experiment where I insert flux here, and the total flux changes from 0 to 2 pi. If I change to some other flux, I get a different system, which will have a whole different set of energy levels. But when I put exactly flux 2 pi, I can just see from this Hamiltonian that nothing's going to change, because if this is 2 pi, I can just shift the momentum by 1 here and absorb that shift. But I can only do that at 2 pi because n has to be an integer.
Okay, yeah. So this is for flux changing from 0 to 2 pi. Understood.
Yes, yeah. So I adiabat slowly. I follow the same state and I insert flux 2 pi and look at the change in momentum of that state.
Thank you.
Okay. All right. So now basically what we're going to do is we're going to make some ansatz for the many-body ground state for a particular system and look at its low energy excitations. We're going to say, well, this is a very slow flux insertion, so this change in momentum must all be due to some very low energy excitation in the system. And so we're going to figure out how much energy is, how much change in momentum is captured by the low energy excitations and equate it to this exact value. Okay. So that's the next step. So this step is completely rigorous. The next step will involve some assumptions. Okay. And you'll get different answers depending upon what assumptions you make about the nature of the many-body ground states. Since we don't have any exact many-body ground state, we're going to look at various examples. So now we're going to make a rather strong assumption, which is the assumption, which is basically Fermi liquid theory. Assume all low energy excitations are quasi-particles, are fermionic quasi-particles of charge 1. unit charge under this charge that's measuring the integer n of charge 1. Around a Fermi surface. Okay. And there are, so these are the low energy excitation. And also, there are no other low energy modes on a torus. This is actually now you can see where we're going with this. For spin liquids, we know there are low energy excitations on a torus. We saw that in topological order. And those will come back to give you a correction to the Luttinger theorem. But for now, we assume they're not there. All the low energy modes are due to the quasi-particles. And what makes this argument not so rigorous is that these are gapless excitations. And so it's not as rigorous as the things we can do for spin liquids with a gap. But it's still a pretty good argument. Okay, so what happens to them? So here then you have a Fermi surface.
Sorry, can you elaborate on the last point about the lack of rigor due to gaplessness?
Well, I mean, because even the quasi-particles have discrete excitation energy, 1 over L. And so you are, looking at all these excitations, the gap of order 1 over L, but taking a macroscopic density of them and summing them over. That's, and you're somehow ignoring also that because of electron interactions, each of these quasi-particle interaction levels actually has a slight width due to damping, which is non-zero. So all of that we kind of ignore. Yeah, that's what makes it less rigorous. But I think, as you'll see, there's probably a way to clean it up, but not the way to the satisfaction of mathematicians, I'm sure.
But I'm not a mathematician, but I just want to understand. So you
Yeah.
had a gap. If the system had been gapped, there wouldn't be a question, and the adiabatic process would
Exactly.
be completely standard.
Right.
But here it's gapless. So as you gradually change phi,
Yeah.
can the state change a little bit because it costs little energy?
Right. So now if you had free fermions, then you can almost make it rigorous because then your energy level spacing is 1 over L between these free fermion states. But once you have interactions, there's a many body level spacing which is e to the minus L, and the interactions do broaden out each fermion, each free fermion state by when you have a finite density of quasi-particles, which you will have maybe just including one flux quantum. Yeah, maybe it's okay. All right. Since you're only inserting one flux quantum, you're not exciting a finite density of quasi-particles. Just how many are you exciting? Yeah, it's relatively small. So yeah, I think it's fairly rigorous. Yeah. Yeah. Okay. Maybe I shouldn't be so cautious. All right. So what's going to happen? Well, you have all these quasi-particles on the Fermi surface, and each one of them are going to feel the flux, and each of them are going to move in momentum by x. So you just take just a very thin sliver of quasi-particles, and you move them over by kx. And you can see that's completely equivalent to moving the whole Fermi surface a little bit. And notice the only changes that are happening are right on the surface. So this is before flux insertion in yellow, and after flux insertion and the appropriate gauge transformation, where the momentum has changed in orange. Okay. So now so the quasi-particles have moved a little bit around this Fermi surface, and now I just have to add up the momentum gained by the quasi-particles and equate it to this quantity. That's all I have to do. And what does it give me? All right, so here I'm going to have to look at my notes, get all the signs right and so on. Okay. All right, so what is this? So the change in momentum, delta px, well, okay, so the way you're computing it is initially you had all the quasi-particles in these states, the yellow states, and now they're in the orange states. And so you just add up the momenta of all the particles here and all the particles there, and subtract the ones over there. So this is going to be sum over all p times delta np times px, where delta np in this region, here delta np is 1, and here delta np is -1. Okay, so now you can see that this is equal to an integral around the Fermi surface, a surface integral of px times, and this thing is delta p dot dsp where delta p is the, what is delta p here? Delta p is a vector which is 2 pi over Lx. Okay, here delta p, that's not in the notes. Dot dsp, where dsp is the normal here. Okay, times the phase space volume, which is Lx Ly over 4 pi squared. Okay, so this is just a bit of bookkeeping, and I'm sure you can check this. It's just a way of computing the positive area of this little shell and the negative area of that shell. Okay, and then adding not just the area, that's this term over here is +1 in this region and -1 in this region, but after integrating over the angular, the radial coordinate, and then you just have the angular coordinate around this direction to integrate over. Whoops. Right. Okay, so now you can use Gauss's law and evaluate this. So this just turns out to be, after Gauss's law, it just turns out to be 2 pi over Lx, which is delta p dot x hat, times the whole volume, Fermi volume of Lx Ly over 4 pi squared times dV. Okay, where dV is the momentum space volume. All right, so there you have it. And so now you take this result here and equate it to that, and you have your statement of Fermi's of the Luttinger relation. Okay. Okay, there's this small issue of the mod 2 pi that you have to take into account. This is a mod 2 pi, and you know here you have n over Lx, where n is of order Lx Ly. This is a very large number compared to the 2 pi. So this is not entirely there. But what you have to do then is do the argument for both directions in x and y and insert some small number integer of flux quanta, which mx and my in the 2 directions, which are relatively prime. And when you go through all of that, and you just look at the generalization of these relations, you conclude, in fact, the correct relationship is that this Fermi volume integral dV over 4 pi squared is equal to 2 pi is equal to n over Lx, Ly, mod, in this case, mod 1, because there's no spin. And this has this, right units. This is units of 1 over area. This is also units of 1 over area. Okay. All right. So that's Oshikawa's argument, a beautiful argument, which, of course, as you can see, is much simpler than Luttinger Watt function and all of that. And its main assumption is right here, but it's very clearly stated because you see exactly what's involved. It's just saying that there are low energy quasi-particle excitations whose momenta shift by 2 pi over Lx. And you just count them for different flux insertions in different directions. And when you put it all together, the only consistency requirement you end up, the only consistent solution you end up with is this one right here.
Subir, a quick
Yes.
question. This whole argument is couched in the language of K-space Fermi surfaces and their volume. Is
Yes.
there anything at all that survives if there's even a small amount of disorder in the problem? So K is not a good quantum number.
Yes, good point. So there are Luttinger arguments in the presence of disorder. That's actually also in the notes. But those arguments, those Luttinger theorems, those Luttinger relations are expressed in terms of, knowing all sets of eigenfunctions of the Green's function at 0 frequency, which are there, and you can compute them in principle, but they're not very useful. It's not expressed in terms of quantities that you can easily measure. But there is definitely a Luttinger theorem, even for disordered systems. I don't know how to do the flux insertion arguments in that case. Yeah, probably it could be done, but in the notes I have written down the statement of Luttinger's theorem for a disordered Fermi liquid.
Okay.
Okay, how am I doing on time? 20 minutes, okay. All right, any other questions? Okay, so now we are to the central point where we're going to put together the first 2 parts of the course. I did Fermi liquid theory and its descendants in the first part of the course. Second part of the course, I did spin liquids, but let's just focus on the simplest case, the Z2 spin liquid, and then ask what happens in a Z2 spin liquids. But we already know there are other low energy modes in a torus for a Z2 spin liquid. And therefore, to get this Fermi volume, so this is now goes to right to Nadi's question, if this Fermi volume is going to be anything other than the right-hand side, there better be another contribution from the Z2 spin liquid, which makes up this rule. You cannot ever change this rule, okay? So what we're going to do is do a flux insertion for a Z2 spin liquid, and then show you that in fact, it has in fact a change of momentum, which is 2 pi over Lx, where n is the number of sites, so density of 1. It gives you precisely the right momentum change. And therefore, in FL star phase, it can eat up exactly the density of 1 on the d sites in the volume of the Fermi surface. Okay, so now we're going to do the Oshikawa's flux insertion argument for a Z2 spin liquid. So here the assumption will be a fermionic quasi-charge run around a Fermi surface, and those of a Z2 spin liquid. So here, this is sort of similar to the perturbation theory and JK argument. We start from JK equals 0, and then we did perturbation theory in JK. And here we're doing this roughly the same thing. We're saying at JK equals 0, I have a small Fermi surface and I have a Z2 spin liquid. Then I turn on any interactions I want between the 2 sectors. And I'm going to show you that this is satisfied if and only if this Fermi surface is small and has size rho c, because the Z2 spin liquid has these stable topological global excitations, which coupling to any other system is not going to affect them at all. Okay, so it's effectively the same as the JK equals 0 perturbation theory argument, but here it's a little, again, a bit stronger because you're making the argument on these topological excitation we know are super stable. So this is 1 over area because volume is 1 over area. And this is also 1 over area. Yeah, so there's a few more steps between, but I think they're all okay. There's an Lx here that'll cancel with this Lx here. There's a few more steps to change the mod 2 pi to the mod 1, but that's a bit of mathematics, which I cannot possibly get right on the board, which is actually in Oshikawa's paper. Actually, there's a nice paper by, I should also mention, Paramakanti and Vishwanath, which probably has the cleanest statement of that step. It's a little bit of mathematics with prime numbers, and relatively prime numbers you can show you get from here to there. Okay, so now we just have a Z2 spin liquid. So there's various ways to do this, and the simplest way I know to do this, and I apologize to students who may not be familiar with it, is to use the language of the Chern-Simons gauge theory. So, and I'm just going to do that. We won't need this for the rest of the course, but let me just view it, and we can discuss later if you want to know a bit of the background. So we just consider only a Z2 spin liquid. So we just have this part, forget about the other part. Okay. And a Z2 spin liquid is described by topological field theory. Which is, it has two U1 gauge field, U1 level, well, topological field theory of gauge fields. I call them A1 and A2. And the Lagrangian is, okay. Okay, is I over pi, it's A2 wedge dA1. So that's the usual Lagrangian. But I'm going to now couple this to an external gauge field plus I over 2 pi. And I'm going to call that A of S wedge A2. Okay. So there's two gauge fields, not A1 and A1 and A2. This is the usual Lagrangian that gives you the properties of the Z2 gauge spin liquid. And this is some external gauge field that's coupling to the flux of A2. And what are A1 and A2? Now, I think you will remember I defined these Wilson line operator. I had the Wn. So Wi is on the X or the Y direction.
Sorry, Subir.
Yes.
Is capital A a 2 form or a 1 form? Or is there a D missing the second term?
There's a D missing.
Okay, thank you.
Yeah, A is a 1 form. So I had these things, Wx was I integral dx of A2x component. No, W is A1, sorry. And I had Vx or Vy, let's say, is exponential I dy of A2y. And these, because of this Chern-Simons term here, these Wilson line operators obey the algebra Wx Vy is minus Vy Wx. So that we derived many different ways. It was, so we can think of this here is that A1 is the Wilson line operator for the spin-ons, or Wilson line for the E particle. And the other guy is the Wilson line for the M particle. Okay. So that's just recalling things we talked about in maybe a somewhat more sophisticated language. You have these two excitations in a Z2 spin liquid, the spin-on and the Vis-on. The Vis-on is the M particle, which has charge under A2. And the spin-on is the E particle, which is charged under A1. These are mutual semions. The E and the M are mutual semions. And that relationship is guaranteed by this term and also by this, which are closely related. Okay, so what is this gauge field here, A sub S? So here I have to be a little careful in these factors of 2 that are really quite crucial. It's all about factors of 2 because if I take away 2 electrons per side, then I'm not violating Luttinger's theorem. So this A sub S is an external gauge field which couples to the spin, the globally conserved spin of the electron. So for this theorem to hold, I do need spin, or at least SZ, to be conserved. Okay, so what I'm doing here is I'm going to do a flux insertion where I only add a flux that acts on, say, the spin up particles and not the spin down. So where is the, yeah, whoops. I hope I can move the board up now. Which way does this go? Maybe you can fix that for me. Thank you. Just have to move the board up. All right. Well. Yeah, okay. So for the original electrons, which make up the Z2 spin liquid or anything else, I have the following gauge fields. I'll only write out the time components. Okay.
Subir?
Yeah.
So would you just explain a bit more why the spin gauge field couples with A2?
Yes, I'm going to explain. Okay.
Yeah.
Right. Okay. Maybe I can explain that now before I. Yeah. So basically, think of. Yeah, let me just say. So I have the original electron, C dagger, I alpha d by d tau, and it's going to couple to the usual gauge field A tau, the usual minus I A tau minus I A S over 2 times sigma z alpha alpha times C I alpha. So there are 2 gauge fields. One couples to the spin component, spin of the physical electron, and the electron has spin 1/2. That's the factor of 1/2 here, and A tau is the unit charge of the electron. Okay. So now this A sub S is the same as that A sub S. A sub S tau. Okay, so what does that tell us? Well, that tells us that the A sub S gauge field couples to the flux of A2. Okay, so the flux of A2 is the flux carried by the Vis-on. Sorry. Oh, okay. Now, if I look at that equation of motion, the spin-on has a flux of A2. Okay, so you have what's happening is here you have the E particle. It has flux pi of A2, and then you have the M particle, and it has attached to it flux phi of A1. That's again the consequence of the Chern-Simons term. So this is telling you that when I take an E particle around an M, it sees the flux A1, and so you pick up -1, or vice versa. So this is telling you when I couple A sub S to the flux of A2, I'm actually coupling to the current of the E. So this is just telling me that the E particle has spin a half. Okay, and that's why that's the 1/2 pi, this is pi, so that gives you a factor of 1/2. Okay, yeah, so I should maybe write that up there. That's a bit taller. So this tells us E particle, well, let me write it here, E particle has spin Sz equals 1/2. Okay. All right, so now I'm going to do a flux insertion of 2 pi with, yeah, okay. So I only wanted to act on the upspin particles. So I'm going to do a flux insertion. I'm going to take AS is equal, let's call this AE. AE times 2 is equal to phi over Lx. So I'm going to insert flux AS, which is phi over Lx, and AE is, phi over Lx, and the net effect will be to put flux phi on spin up particles and no flux on spin down particles. Hopefully I got this right. All right. So now, this is the final PS resistance. Now I recall a very important relation that we all had deduced a while back for the effect of translations on a Z2 spin liquid. So in a Z2 spin liquid, we had looked at the effect of translation on this Wilson line operator Vx and Vy. And what we had concluded that Tx Vy was -1 to the Ly times Vy Tx. Okay, so this is a non-topological information that the Chern-Simons theory doesn't know about, but it's, if you wish, some kind of anomaly associated with the underlying Z2 spin liquid on the lattice. But if you translate the Wilson line operator Vy by one lattice spacing, you pick up a factor of -1 to the Ly. And if you remember where this came from, you had this, Vy was a product of sigma x operators on these links, and you moved it over here, and you end up getting the product of sigma x operator on these sides. And then you had the relation that product on sigma x on each side was -1 from the constraint that you have 1 particle per side for the odd Z2 spin liquid. So this is exactly what we need here. Okay. So now all we're going to do.
So this is only in the phase where it's -1, not in the phase where it was +1.
Right. If you take the phase +1, then you have an even number of integer spin, which correspond to even number of electrons. And in that case, there's no difference between the small and the large Fermi surface, at least in terms of the volume mod 2. So you won't get any contribution, but that's just fine. There can still be a FL star phase, but its Fermi surface volume is not anomalous if you have an even integer spin liquid. For an odd integer spin liquid,
if we change Ly by 1, we just add another layer of sites.
Yeah.
What is going to happen?
This is going to oscillate. So we want to apply this for all possible values of Ly. We want to equate this to, okay, the delta Px that's gone for all possible values of Ly. It has to hold for every Ly, and we're going to use that fact. All right, so what's the time? 4 minutes, okay. So let me just finish this argument here. So now we have Ax, this is phi over Ax, okay. So I'm just going to take that large term in real time. So the time evolution operator which is that u, which is exponential of I of d3x of epsilon mu nu lambda a as mu d mu a2 lambda. Okay, so we know what a sub s is. It's right here. And let's just call A2, we're going to take it spatially uniform. We take A2y is some theta y over Ly. So here's my A2. Here's my A sub s. It's only the x component here. Okay. So I insert this A2 and this A sub s in here. I can do the integral. And you see this just becomes e to the I theta y, which for this A2 is exactly Vy. So the effect of time evolution of the flux insertion of 2 pi gives us, the effect of that is to put a Wilson line Vy on the torus. So if I can draw this, this is really the main point.
Sorry, what if this u, so you say it's the time evolution operator, is it a function of time?
No, so I'm doing this flux insertion adiabatically, and I'm just evaluating the time evolution operator for that process. And I'm just
so it's
taking
the integral of the time evolution.
d3x, yes.
So when you wrote time evolution operator, u is not the time evolution.
What did I do? I made a mistake. Okay. No, it is. So you get a d phi dt, you get a d theta dt, and you integrate over time, it just becomes e to the I theta. If you want.
My question is about the words that you wrote on the left.
Okay.
Time evolution operator?
Yeah, so this is I'm doing a time evolution where I'm inserting flux from 0 to 2 pi, and it's the operator that performs that evolution. The flux insertion operator, okay. Maybe that's better. All right, so what we have done effectively, if I just draw it in pictures. So here's my torus. So here's a torus. So I insert flux phi, it goes from 0 to 2 pi in the whole of the torus. And the net result of inserting the flux is I have inserted an operator Vy on this cycle of the torus. Okay. All right, so now you're basically done. So this is the flux insertion operator, which is precisely Vy. And now you can see from here that the effect, the momentum eigenstate, therefore, the momentum carried by this flux insertion is exactly 2 pi over Lx, which is the flux carried by 1 particle per site. Times, yeah.
I'm sorry for being so slow. The right-hand side.
Sorry, I'm going very fast. Yeah, go ahead, please.
Vy on the right-hand side of the last line is an operator acting at time t. Also, the commutation relation of Tx and Vy that you wrote, these are operators acting at a particular time.
So you have some, you have some initial state psi, then you insert the flux, and you get some final state psi prime. So this is time evolution, adiabatic time evolution. And you end up with some other state psi prime at the end of this evolution. And all I'm saying is that psi prime, the final state, is just Vy times psi. That's what this operator in the topological field theory tells you. So I insert the flux. I have some state. I insert flux. in this hole of the torus, and this type of flux. And what I end up with is a different state, which has got an operator Vy acting on it. Okay. So now you want to evaluate the momentum of this V of psi prime. And so that's going to be Tx times Vy times psi. And now I use the commutation relation, which is, so that gives me -1 to the Ly times Tx Vy times Tx acting on psi. Okay. But Tx acting on psi, we know this has state of definite momentum. So this is equal to -1 to the Ly times Vy times e to the I initial Px acting on psi. And then this I can write as, wherever. I have to get all the factors right over here. Yeah. So this turns out to be, okay. E to the 2 pi, e to the I pi Ly times plus IPX times psi prime. So the momentum of the state psi prime differs from the momentum of the state pi x by this extra factor. Okay, and now you just work that through and all of the factors of 2, which is in the notes, and I'm out of time. But I think all the factors of 2 are correct in the notes. You get back exactly the statement of the Luttinger theorem for the FL star phase, that the contribution to the right-hand side of the momentum balance equation is precisely that of a Fermi surface with a density of 1 electron per site, with spin up and spin down. Okay. All right, so now you can see why this particular relation is so important for everything. It was initially seen as some kind of constraint on the structure of odd Z2 spin liquids and led to all kinds of complicated theories of confinement. And it's also exactly the relation that allows you to get a more exotic Luttinger theorem in the presence of a spin liquid. Okay. All right. So thanks a lot. See you on Wednesday. Any other questions at least? Yeah, go ahead.
I think what happened was that in the expression for you integrated over time as well, right?
Yeah, so it's the full time evolution operator. It's basically, the time ordered exponential of this operator is exponential of I integral d tau h of tau time ordered. So I'm just, that whole operator is what causes the flux insertion. And that operator is basically the Lagrangian, which is right here. And I just evaluate, I did the time integral.
It's not explicitly dependent on time, so yeah.
No, so sorry. So this is function of time. So this is the final value of theta y. So you get you'll get a d theta dy. So this thing, yeah, there's one more step here. Maybe I should have written this. This turns out to be exponential of I d tau dt d theta y dt. And then you can do that integral, and that's what I got. Yeah, that's where the time dependence is. Sorry, thank you. The time dependence is in A2 because that's, the time dependence in AS, and I also allow AT to be time dependent. Everything is time dependent, and I just do that. Okay. Yeah.
if I wanted to do the same argument for a Yuan spin liquid, there
Yeah.
would be also the low energy photons.
Right.
Can one prove that the low energy photons do not carry away any momentum? There is not any extra momentum.
No, you can do this for the photons too. That they'll have to rearrange in a way that gives you exactly this momentum. Yeah.
I see.
Yeah.
So
right. If you have a U1 spin liquid, there's also some fermions there. If it's gapless,
yeah.
then
So that was going to be
it
the
has
next
to be.
slide.
I think if you have a U1 spin liquid, you probably have to worry about the matter fields more carefully.
Yes.
And it's the spin-on matter fields that will carry the momentum there. But for a Z2 spin liquid, you can state it quite abstractly in terms of the off the gauge fields.
But also I'm more precisely thinking about the spin-on Fermi surface state, for example.
Yeah.
And there this momentum can be carried away by both the fermions as well as the photons.
Again, I think you start from the case where the spin-ons are free, and then you have the right momentum, and then you argue that when you couple them to gauge field, nothing's going to change. I mean, it will depend a little bit on the PSG of the photons, right? If the photons have a trivial PSG, which is what they have in a spin-on Fermi surface state, then the photons don't carry any momentum. It'll all be just the spin-ons. But if the photons have some non-trivial PSG, then that will also change the shape of the spin-on Fermi surface. And yeah, you may have to consider both of them in some complicated way. Yeah. Yeah, so it's a complicated argument. I think I like the first argument. As you can see, I'm more comfortable with it. But anyway, this has the advantage of tying in very naturally and making a connection to these type of relations and how they're. I think there's a paper by Dominique Elzen-Senthil recently, which does this in a very sophisticated way using all kinds of SPT phase technology. I don't understand much of it, but it's a very nice paper. And the key really is making a connection between this flux that you're inserting. The flux that you're inserting is you're gauging some global symmetry. And that's what you insert at the outset. And that flux insertion has an action in the low energy degrees of freedom of a spin liquid, which do not carry the global, which is the action of Vy, which is not the global symmetry, it's it's some kind of emergent gauge symmetry. And so what's happened here is that the mutual Chern-Simons term was crucial. It connected the global symmetry to the internal symmetry. So this is what they call as there's some kind of homomorphism between the UV group and the IR group. And to figure out that homomorphism, really you need to know something about the structure of the spin liquid. For this particular Z2 spin liquid, we know everything about it, and in particular this property, and we can see how it all works out explicitly. Okay. All right, great. Thank you. That was fun.